Okay, so I was asked to talk about tidal disruption events in the era of Axis, and I had a lot of fun preparing this talk, and I really hope to get into what we expect in the next decade. So tidal disruption events were originally a theoretical prediction and a new way to discover dormant black holes lurking in the centers of galaxies. And in particular, they are sensitive to lower mass black holes, around 1 million to 100 million times the mass of the sun. And this was first beautifully laid out theoretically by Martin Rees in 1988. But I'm happy to say that tidal disruption events are now an observational reality, and I'll be showing you why. So what happens when a star ventures too close to a black hole? Well, the tidal forces of the black hole will overcome the self-gravity of the star, and it'll get ripped apart. And you can determine how close a star has to get to be overcome by tidal forces. And that radius shown here, known as the tidal disruption radius, depends both on the mass of the black hole as well as the mass and radius of the star itself. And so you can see that it depends both on the type of star. Is it a main sequence star? Is it a very compact white dwarf or extended red giant? And how big is the black hole? And in fact, a fun aspect of tidal disruption events that make them such a sensitive probe of lower mass black holes is that for the very large black holes, the event horizon actually is outside, or the tidal disruption radius is actually inside the event horizon. And so a star will be swallowed whole before being disrupted around black holes greater than 10 to the 8 solar masses. So tidal disruption events are a really fantastic probe of these lower mass black holes. And that is specifically where we have the hardest time finding observations to directly probe the masses of black holes and then compare them to their host galaxy properties. So shown here is the famous black hole sigma relation, where you see the mass of the black hole versus the velocity dispersion of the host galaxy bulge. And these lower black hole masses, we have very few dynamical black hole measurements. And so tidal disruption events are an exciting complementary probe. So when the star is disrupted, the gas from the star, some of it is ejected at high velocities, but about half of the stellar debris returns around the black hole and shocks and circularizes to form an accretion disk. This compact accretion disk radiates in the soft X-rays in the UV and produces a luminous flare of radiation. And numerical simulations of this fallback process predict this very well-behaved t to the minus 5/3 power law decline, as well as a tight relationship between the time at which the mass accretion rate peaks and the black hole mass. So this should scale as the black hole mass to the 1/2 power. And so in principle, tidal disruption flares should be a way to weigh the masses of black holes in the centers of galaxies. In addition, you'll see here the dashed lines show the Eddington limit for black holes of 10 to the 6 to 10 to the 8 solar masses. And you can see that for the lower mass black hole systems of 10 to the 6 solar masses, for example, the peak mass accretion rate is several orders of magnitude above the Eddington limit. So these are also great probes of super Eddington accretion. Tidal disruption events can also probe the stellar populations in galactic nuclei. Here I show, of course, our own galactic center and its rich population of stars, some of which may approach close enough to be disrupted. And depending on the type of star being disrupted, you're going to get much different peak mass accretion rates as well as time scales. And so in principle, you can distinguish between these different types of stars. The rate at which tidal disruption occur depend very much on the nuclear stellar density of the host galaxy. And in fact, these are quite rare events, only once every 100,000 years or so in a given galaxy. So we have to work very hard to find them. So we use wide field surveys, surveying millions of galaxies. But there are indications that given this sensitivity to stellar density, it may be that in the higher redshift universe where we see evidence for more compact stellar nuclei, that we could expect quite high tidal disruption event rates. So we're currently in the era of large surveys across the electromagnetic spectrum. And this is fortunate in that we've been able to discover tidal disruption events using various methods, because we now know that tidal disruption events indeed are multi-wavelength emitters. They show soft X-ray emission from the inner accretion disk, this compact disk that forms from the tidal debris. They show a luminous UV optical component that we're not sure exactly what it causes it, but it's coming from outer, larger radii, perhaps from the debris streams reprocessing the inner accretion disk emission. We also see transient mid-infrared emission from a dust echo, from dust that happens to be in the vicinity that reprocesses the UV radiation. And then sometimes we see evidence of radio emission from a jet or outflow. We're currently in a golden age specifically for wide field optical surveys. And most of the work I've done recently has been using the Zwicky Transient facility, which you can see here has a very impressive 47 square degree field of view. And we've really amped up the rate at which we're discovering TDEs. When I first started in this field, we were finding about 2 TDEs per year. Now we're on the order of tens of TDEs per year. And with these optical surveys, we've really come a long way in characterizing tidal disruption events, both in their light curve shapes as well as their multi-wavelength properties. And that's because we've been able to discover them in real time and with an excellent cadence. So shown here is the contrast between the first X-ray candidates that were found using X-ray surveys and now with our optical searches. So with these increasing samples of TDEs, we've confirmed that indeed we see a drop-off in the number of tidal disruption events as you go to these higher black hole masses, consistent with the presence of an event horizon. This is showing a study before ZTF, a compilation of only 12 tidal disruption events from various optical surveys. And now after ZTF, we have much better statistics, and you can really start even probing the underlying black hole mass function that is producing these events. But enough about the past. I'm really here to talk about the future. And I'll tell you that the future is bright. So already in 2030, we're going to have a very exciting ecosystem for studying tidal disruption events. We're going to have this trio of capabilities in the UV and optical that are going to be really fantastic. Ultrasat, which is going to be launching in around 2027, 2028, is an Israeli mission that is going to be doing all sky near UV cadenced imaging, as well as high cadence imaging with a timescale of only 5 minutes over 200 square degrees in the near UV band. We'll also have the Rubin Observatory operating on the ground, doing multi-band, deep cadenced optical imaging, as well as producing very deep static sky imaging. And then we have the UVEX Medium Explorer mission from NASA, which is launching in 2030 and is going to provide both all sky, far UV and near UV cadenced imaging on the timescales of hours to months, as well as a very powerful target of opportunity UV spectroscopy capability. And so these 3 surveys and facilities operating together are really going to produce thousands of tidal disruption events and are genuinely tidal disruption event factories. And I just want to highlight here, I'm on the science team of UVEX, so I have to advertise the exciting capabilities, especially for time domain science, which I'm focused on, both the wide field UV imaging, which is going to be 100 times the depth of GALEX in 2 bands, but with an improved spatial resolution of 2 arcsecond PSF, as well as this long slit far UV and near UV spectroscopic capability that we will be able to respond to transient events on the timescale of hours. So I've submitted with some colleagues a general observer program idea for AXIS, which is really focusing on the many AXIS and UVEX synergies in the area of TDAM, which is time domain and multi-messenger astrophysics. And the fact is, that if you study energetic transients, you know that they are bright simultaneously in the X-rays and UV. And so with AXIS discovering in the X-rays and being able to rapidly respond to these AXIS discoveries with UVEX within 6 hours in the UV, as well as UVEX discovering transients in its far UV and near UV imaging with the possibility of then rapid response from AXIS in the X-rays, you're going to enable a whole new era of joint UV and X-ray studies of the earliest phases of supernovae, rapidly evolving transients such as LF bots and kilonovae, as well as monitoring observations of long-lived transients such as tidal disruption events and changing look at AGN. So there's a really rich astrophysics that you can do with these two facilities together. But let's put on our brainstorming hats and think about what will the TDE landscape look like when AXIS launches in 2034. And you may recognize this image. Does anyone know what this is? The Jetsons, yes. So we're getting there, maybe with the flying cars. But when preparing this slide, I didn't realize how good it's going to be. So in 2034, Rubin will have almost completed its legacy survey of space and time and detected almost up to 10,000 TDEs out to redshift 2. Roman will have completed its 5-year baseline mission, detecting 100 TDEs with excellent light curves out to redshift 4. Ultrasat will have completed its 3-year prime mission, detecting another 10,000 TDEs out to redshift 2. UVEX will have completed its 2-year prime mission, detecting an unprecedented number of 1 million TDEs out to redshift 3. Now that number is very high because of the depth of UVEX, but the cadence of those discoveries they won't be very equally sampled. So you'll be able to discover 1 million TDEs for follow-up, but you may not be able to use the UVEX data alone. And then LISA will be close to launch and could potentially detect a white dwarf intermediate mass black hole TDE in gravitational waves in the local universe. So I was trying to imagine what this is going to feel like to me in 2034, and this pretty much sums it up. So all of us should be feeling that we're really diving into an epic of abundance, specifically for TDEs, and hopefully also of money. I don't know about that. Okay, so with tens of thousands of TDEs being discovered by all of these facilities, what should AXIS do? It will have to make some wise decisions. So one thing you can do is follow up specific subclasses of tidal disruption events. And I just want to show you what we've found from following up optically selected TDEs from ZTF. So one thing we find is when you follow them up with something like XMM Newton or Swift XRT, you see that they are very soft in the X-rays, and they really have, they're kind of boring. They all look like very soft thermal spectra with almost all of the photons below 1 keV. However, while their spectral properties are quite similar, they show a wide diversity of behaviors in the time domain in the X-rays. So some show X-ray emission that declines with the power law along with the UV and optical, but others show initially faint soft X-ray emission that then dramatically brightens with time. And so here I show that there are two populations, those that show emission from the X-rays that is consistent with the disk together with the UV, and others that show dramatic changes in the UV to X-ray ratio from the UV dominating to then having a more similar ratio. So what is causing these dramatic X-ray light curve behaviors? We're still trying to determine that. They could be due to various processes, including viewing angle effects, reprocessing, delays in the actual circularization of the debris streams into a disk, or patchy obscuration. We've argued from a very nice study from my graduate student, Muriel Guolo at Johns Hopkins, that if you look simultaneously at the UV optical and X-ray spectral energy distributions, they actually do show the process, the features of reprocessed emission, and that at later times you can then see it evolving to a spectrum that's more like just a plain disk. So I can't forget, if I'm in an X-ray, giving an X-ray talk, that of course there's a really exciting subclass of TDEs that don't just show soft X-ray emission, but in fact show very luminous hard X-ray emission as well as luminous radio emission. And these have been discovered in the nuclei of a few galaxies by SWIFT in the hard X-rays and by ZTF in the optical, and then found through X-ray and radio follow-up. And about only 1% of TDEs show these features, and they have been interpreted as the result of an on-axis TDE, where you're looking down the barrel of a relativistic jet that was launched by the system. Okay, so in addition to follow-up of TDEs, in particular, you can look at very late times in the X-rays, simultaneously, for example, with UVEX imaging, to actually model this compact accretion disk that gets formed in the tidal disruption event, and actually get parameters such as black hole mass and spin estimates. And again, my graduate student, Muriel Guolo, has already started doing this with an old tidal disruption event, Assassin 14 Li, where he simultaneously fit the UV optical and the soft X-ray emission, and was able to actually fit for the outer radius of this compact disk, and found that it was consistent with what you'd expect for the circularization radius for a tidal disruption event of the black hole mass of this system. So this is really exciting, sort of detailed disk physics that you could do at late times in tidal disruption events with careful joint UV and X-ray observations. There's also a very fun result that if you look at very late times, the UV emission from this disk tends to plateau, and you can actually use the plateau luminosity to infer the central black hole mass, because there appears to be a strong correlation. Okay, another thing you can do is use AXIS to monitor old TDEs for the emergence of QPEs. We really love acronyms in our field, and I'm only going to briefly talk about this because we're going to have a very nice talk soon in the session about QPEs, but they're really a fantastic, as of now, X-ray only phenomena, and it's very exciting that recently they were discovered to emerge in the late time X-ray monitoring of a known nearby tidal disruption event. And there have been subsequent other discoveries that you'll hear about. And shown here is just a zoom in on what these X-ray periodic eruptions look like. And again, this is something that AXIS could do. You could also use AXIS to discover tidal disruption events, and in particular, not depend on all these other wavelengths, but really discover them in the X-rays. However, the numbers are not going to be huge, so we're not talking thousands or hundreds of thousands. We're talking more like tens of TDEs from my calculations using some AXIS surveys. So these are going to be comparable to the numbers that eROSITA is finding now, but to higher redshifts, which may be interesting. And just to remind you that at eROSITA, again, which has this spectacular wide field view of the soft X-ray universe, has indeed been discovering TDEs on the order of tens of them. And they're finding that they have the same host galaxy preferences as the optically selected TDEs, so they seem to appear to prefer Green Valley host galaxies. And we've also been able to combine the X-ray selected and optically selected TDEs to get the intrinsic X-ray luminosity function of tidal disruption events. There's been a more recent sample from eROSITA also published that also shows these preferences for the Green Valley. Okay. Another thing you could do with AXIS is follow up extreme TDEs. These are TDEs around intermediate mass black holes, perhaps binary supermassive black holes, off-nuclear supermassive black holes or black holes at very high redshifts. And indeed, we're entering a golden age of infrared surveys with the launch of Webb already producing fantastic results in the near-infrared and mid-infrared, and then with the upcoming Roman wide field survey in the near-infrared. And my graduate student, Mitchell Carman at Johns Hopkins, has already been predicting the expected yields of tidal disruption events using these infrared capabilities with the specific goal of capturing the fact that these UV bright tidal disruption events, actually the peak of their emission as you go to higher redshifts slides into the near infrared and mid infrared bands. And so, for example, a UV bright TDE is actually visible by JWST out to redshift 10 in the mid infrared. And so we expect to be able to detect tidal disruption events with Rubin out to redshift 2, Roman out to redshift 4 or so, and with JWST really out to very high redshifts, out to 10 or 11. And we've already started to look for these very high redshift TDEs by looking for point sources of specific colors in the James Webb Cosmos survey. And my student already has an exciting redshift 5 TDE candidate where we think it's a point source because we don't expect to be able to detect the host galaxy, but we do expect to see the UV bright TDE in the JWST bands. And so we're following up this source with spectroscopy in a few days. There's also, so AXIS will be able to follow up these exciting high redshift TDE candidates thanks to its excellent X-ray sensitivity. There's also an entirely new development of now several examples of off-nuclear tidal disruption events. So as we look in optical surveys, we tend to specifically look at transients in the centers of galaxies. But if you open your eyes to all sorts of transients and you don't get overwhelmed by supernovae, you can start to search for tidal disruption events around black holes that are wandering in the halos of more massive galaxies. And so initially, there was actually a detection back in 2018 from archival observations by Chandra that indeed detected an X-ray flare, but there wasn't a redshift confirmation of the source to confirm that it was indeed associated with the central galaxy. However, more recently, an Einstein probe discovered an X-ray transient, which was shown to be significantly offset from the nucleus of this more massive galaxy. And underlying, there's a very faint galaxy host. And it was also showed to have an optical flare, as well as, I forget if it had radio detection. And then more recently, ZTF detected an off-nuclear TDE, which this time doesn't show any underlying emission, but it really appears to be offset and wandering in its host galaxy. So when you look at these three systems, what's really fun is the central galaxy you expect to have quite massive black holes that would not be able to disrupt a star. But these offset TDEs appear, based on their X-ray properties, in fact, to be genuine intermediate mass black holes, so less than 10 to the 6th solar masses, maybe down to 10 to the 5th solar masses. And what's nice for AXIS is that their offsets are on the scale of 1 to tens of arc seconds, so certainly within the spatial resolution capabilities for follow-up. Okay, so this is just a summary of all the things that AXIS should be able to do. And thank you very much.
All right. Yeah, Julia. Thank you for the nice talk. I was wondering what your thoughts are around detecting lens TDEs, maybe not necessarily, only for AXIS, but in general with upcoming.
Right, so JWST is already finding several examples of lens supernovae. So one thing to think about are the rates. Given that the TDE rates are maybe a factor of 100 less than the supernova rates. And then I also wonder, since a TDE normally is in the center of the galaxy, if in the lens system it would be harder to morphologically identify the TDE. Because I don't know if you'd have a lot of time domain information, so you might also be a little bit wary of an AGN that could be variable. But it's definitely, I think I would start with the rates and then see if it's feasible.
So the off-nuclear TDEs are really interesting. So how do you distinguish them from supernovae?
The X-rays. So in this case, so X-rays are rare, and so this source was discovered in the X-rays, and then it's interesting enough to follow up and get the multi-wavelength follow-up, and it has the properties of a tidal disruption event also in the UV and optical and its spectrum. The ZTF source, it was just it wasn't too off in that it was still sort of within our general search radius. I mean, Yuhan Yao led this. She knew it was a little off nuclear, but she still, it was nuclear enough that it was surpassed our filters, and it also had the properties of a tidal disruption event in its light curve. And then, of course, in the follow-up with the radio and X-rays, you confirm that it is a TDE. But we're very good about distinguishing between supernovae and TDEs from their optical light curves. But you just are dealing with a lot more contamination as you go off nucleus. So you have to just be more careful, and there's just more chance that it could be a weird supernova. So it's harder work. But the X-rays, you don't have that issue.
Okay. I actually wanted to ask a little more about this, these off-nuclear TDEs, because, besides the fact that they're really interesting from the time domain standpoint, I've been interested in off-center and roving black holes for a while. Dan Batcheldor and I published a paper back 15 years ago, actually, showing that the black hole of M87 is actually slightly off-center in its host galaxy. Not by that much, but by something like, a few tens of parsecs. And this was from HST imaging. And so it's a really interesting question. How many of these guys are there? And, how far away they are, because this is something we know that mergers occur. We know that there will be roving black holes that occur as a result of these. How many of them are there?
Yeah, so I think axis follow-up, like smart axis follow-up of optically selected samples, could answer that question.
I'll try to make this quick, and Suvi, you may not be the best person to answer this, so I apologize if that's the case. You just mentioned the need to maybe identify the sources quickly in the X-rays when they go off as transients. So what is Axis thinking about in terms of automated analysis of all Axis data, not just surveys, but all Axis data, looking for transients compared to deeper Axis data itself to actually trigger the newest?
So maybe that's a question for me. That is something that we are talking about as like a science enhancement option. You get to request, those kinds of additional analysis tools. All data will be available in the archive and pre-processed. So you'll have events files within a day. So you could do it yourself. But yeah, and we're talking about faster transient pipelines, but nothing has yet been decided.
I just encourage the community to not try to do this individually all by themselves, but to work together to not duplicate efforts.
Couldn't agree more. Yeah. All right. Well, let's thank Suvi again. Next up, we have Michela Negro, who's going to tell us about giant magnetar flares.
All right, let's start from the beginning. Thank you for having me here. So I'm very excited about Magnetar giant flares. The assignment was take your favorite science and see what Axis can do for you. This is what I did. Spoiler is going to be challenging, but now you're stuck with me for the next 30 minutes or so, and I'm going to tell you why. So I'm not working alone with this. Zorawar Vadyasingh and George Jonas are also helping. And I've consulted different people for help with different aspects of this. First, I'm going to tell you why I'm excited about magnetars. Because magnetars are the answer. If you have something that probably you don't know what it is, statistically, it could be a magnetar. Since the beginning, magnetar were the answer behind anomalous X-ray pulsars and soft gamma ray repeaters, and then they got merged together in this common origin. And then we noticed magnetars could be the origin of some of the FRBs. We also see magnetars from outside our galaxy, and they show up, I will tell you this later, as a short gamma ray bursts. So a fraction of short gamma ray bursts are from magnetars. There are ideas, models about explaining some of the other isolated neutron stars that appear kind of weird as magnetar themselves. Magnetar could generate gravitational waves. There are models predicting this. And neutrinos. One of the latest excitement around magnetars have been our processes observed from magnetar giant flares specifically. So magnetars are those kind of objects, astrophysical objects that can put together and excite at the same time astronomers and physicists. So these are kind of cool to look at. Why? Because they are very extreme. So magnetars are neutron stars, so per se they are very extreme objects. They have the densest matter that we know of before, of course, becoming a black hole. So that is extreme on its own. But on top of that, they are even more extreme than regular neutron stars because of their magnetic field. So this is a very outreachy slide that I actually show in outreach talks, but you can focus on the more sciencey numbers. That is the magnetic field around neutron stars. There's a comparison. There's 100 million Tesla for a regular neutron star, and for a magnetar, we are talking about 3 orders of magnitude higher. So in this extreme environment, physics really doesn't hold up, the physics that we know. Atoms become like kind of a needles, and vacuum becomes birefringent, like it can polarize the light. So very extreme things can happen, QED effect, so very fascinating objects. They spent the majority of their time in quiescent state. Here I take advantage of this slide just to show the population that we have in our galaxy that we know of. So we know about 30 magnetars in our galaxy, and in the local structure. So we know one in the Large Magellanic Cloud, one in the Small Magellanic Cloud. We have now a population, and we can compare with regular pulsars. So you can see they have typically a long period, seconds long period. They have a very high spin down rate. It means that this magnetic field kind of drags them and slows them down faster than other regular pulsars. If you look at the magnetic field, of course, I said it's extreme. What it tells you, the last plot on the right, on the x-axis, there's this proxy of the age of a pulsar. And it tells you one important thing. So magnetars are quite young. 10,000 years or so. Afterwards, they kind of lose this powerful magnetic field, and they are not magnetars anymore. They stop being active. And what's important, of all these known galactic magnetars, they have been discovered mostly thanks to their transient activity. So the quiescent state is quite faint. even in X-rays. And they show up, these magnetars show up, appears when, for short time scales, they brighten up and they reveal themselves. So this is thanks to the monitors, hard X-rays, soft gamma ray monitors that have been able to catch these signatures. That's how we collected this population in the galaxy. Only Swift detected, in 20 years, detected more than half of the magnetars that we currently have. So the magnetar transit activity is crucial, and it's what is exciting me the most, especially in the context of TDM, right, time domain. So there are different flavors of transient activity the magnetars can have. There's short bursts. These are millisecond long flashes of hard X-rays, soft gamma rays. And here you can read the energetics involved, the luminosity. There's a longer, longer period outburst, that's how we call them, in which, again, the flux from the X-ray flux, the luminosity from these events can become brighter, up to 3 orders of magnitude even. During these outbursts, sometimes we observe storms of bursts. And in one of these storms, for example, we detected also concomitant FRB in one of these magnetars. But what I'm going to focus the most is this particular type of transient activity, which is the giant flares. So let's look at them more closely. These are the most powerful transient that a magnetar can emit. So here are the 3 magnetar giant flares that we observed nearby. One from the Large Magellanic Cloud in 1979, and 2 from our own galaxy in 1998, and the latest one, 2004. They are all characterized by a very bright peak, which is also millisecond long, and a periodic cooling and dying in time tail. The spike of these emissions is so bright that from these galactic events, all the monitors and instruments that were around there got blinded by it. Actually, one of the most remarkable measurements that has been done was by one Russian satellite that was behind Earth, so couldn't see the burst, but detected the reflected light from the moon of this burst. So they actually weren't blinded. They could constrain better the energetics from this bright peak. That is only a few, tens of milliseconds long. And then you can observe this tail that is decaying in time and is characterized by this oscillation. And that is the period of the neutron star that is slowly rotating, and there's this fireball that is trapped there, and you keep seeing and unseeing as it rotates in and out. So the questions are, how many of these magnetar giant flares can happen in the universe, anywhere, okay, not only in our galaxy? What is the mechanism that can produce them? That's about the physics of it. What can generate this burst? And do they repeat? These are clearly the magnetars still there afterwards. Those magnetars that emitted the magnetar giant flares are still there. So these are not disruptive events. They could repeat. So far, we haven't observed repeating objects, but they could. And they, of course, can inform about the energetics and the physics of the inside of the magnetar. About the tail, there are other questions. If you look at only these 3 observed objects, the value of these isotropic energetics seem similar to each other, so 10 to the 44 or so. So the question could be, are these standard candles? And of course, this is a very relevant question. And how far can current instruments see this tail? And because the bright peak is a beamed, we have evidence that it's a beamed emission. What if this happens when it's out of our field of view, but we could still see the tail? We should be able to observe orphan tails from these magnetar giant flares. Here's the status of the current population that extends the magnetar giant flare from our galaxy or local neighborhood to extragalactic distances. So you can count them, and you just need 2 hands for this. There are 9 of them so far, and clearly the great advancement of this has been the use of different monitors, and in particular the IPN interplanetary network that was able to pinpoint the location of this burst to a few arc minutes. This is crucial to understand if they are coincident spatially with a star-forming galaxy, because this is the way that you can understand if they are not cosmological GRBs that are expected to be so far away that you don't see the host galaxy. If you see an event like this and it's coincident with a local galaxy, the chance coincidence that is just an alignment, pure chance alignment, it's very low. So here's the current status, and so the questions here are why Axis could be useful for this. What can improve here? Well, if Axis could see this event, this could be the first arc-second localization of extragalactic magnetars beyond the Large Magellanic Cloud. And why is this important? Well, this is relevant because you could pinpoint the location within a galaxy of this magnetar, and see if magnetars are only found in high star-forming regions. And this can inform about the progenitor, which is the ultimate question: what the hell can produce these huge magnetic fields, right, of these very extreme objects? For farther distances, local galaxies, then you can do some more strategic and systematic study on the galaxy population that host magnetars, and see, for example, if there's a dependence on the metallicity. And this will be relevant in a second, in a few slides. So also current estimates suggest that magnetar giant flare repeats. This is according to the rates that we estimate, but no observation so far. So if Axis could spatially resolve a magnetar location within a galaxy, and then we have another magnetar giant flare from the same galaxy, and this happened from Sculptor just recently. So in that case, we would know, and we would detect if, we could tell if this is a repeating magnetar giant flare. And of course, this has implication on the reservoir of energy of highly magnetized neutron stars. So with more and further detection, we could study how well star formation rate trace the magnetar population, because this is the assumption right now. But this can provide information on the progenitors and answers the question, what's the physics behind the formation of these extreme objects? Okay, so let's do this exercise. Short spikes. I've told you something about them. These are very fast, so too fast to repoint. So the question is, can Axis detect them serendipitously in the field of view, pointing anywhere in the sky? And then we will go to periodic tails. These are longer, so it could be easier to follow up. The question is, are they bright enough to be observed from extragalactic objects? And then the last part is about this nuclear decay, the latest, I wouldn't call it discovery, but more realization about the magnetar giant flare emission of this very late, that peaking at 1,000 seconds after the main peak emission from nuclear decay. Starting from spikes. So the first thing that we have to account for is that these spikes have Compton-I spectra that peak at much higher energies than the axis band. So you have to account for the fact that the energetics that are given are in a bolometric energy range between 1 and 1 keV and 10 MeV. So switching to axis range, that's the energetic that you have to, the luminosity in the X-ray band that you have to account for. And that lowers the numbers that I've shown you so far by 2 orders of magnitude. The next step is, well, then what is the maximum luminosity in axis band that we can, we have observed so far? And this number is a 10 to the 46 Hz per second. And with this, the question is how far can axis detect these luminosities in a short amount of time of the spike, 64 milliseconds, let's say. So with this number, and assuming the sensitivity for roughly 64 milliseconds, the maximum distance is quite interesting, is 692 megaparsec. The farthest observed event now is a 4.5 megaparsec. All right, so let's continue the exercise, because now we want to know how many of these objects we have in the field of view randomly. And this number needs the ingredient of the volumetric rate. We know how the comoving volume is evolving with distance. And we have an efficiency that is basically the sky fraction observed by axis. And I assume the 95% efficiency just to remove slewing time and times that we don't really use the telescope. This is not all, because then what we want is actually the number of detection, not only things that happen in the field of view. And this is more complicated because these events follow an energetic distribution. And this is kind of like a power law in which you have a lot of fainter events and just a few brighter events. So you have to convolve by that. And this is the exercise. And basically, it says that it tells us that axis could detect magnetar giant flares out to 55 megaparsec, basically all of them. Only the 40% brightest ones out to 100 megaparsec, and only 10% brightest within 300 megaparsec. And then basically you detect only the very brightest ones. So the rate of them, it's low. By doing this and doing the calculation, you can then determine the cumulative number of events that you can detect in 5 years out to the distance. And unfortunately, the number of detection is not 1. So the field of view is too small. So despite the fact that we could have 8 roughly events in the field of view, we might not detect any of them. So, and this is because it's quite rare to have a nearby galaxy where you can detect also the fainter events within the field of view, but you could be strategic about it. Also, I haven't checked how many local galaxies are in Chandra's field of views. For any observation, this could be something to check, because that could enhance the chance to get this, but it's hard. Caveats, this calculation doesn't include, for example, the fact that the fainter events are also softer. This goes in the right direction with the fraction of lux fluence in the X-ray band. And I don't account for the evolution of star formation with redshift, which also goes in the right direction. But I'm not sure we're going to get to one event. More interesting are the tails. The tails are longer in time, so we could follow them up. And so here I repropose the same plot of the tail from the 2004 event, but also in the plot on the right, you can see the typical temperature of the black body spectrum, which falls better in axis energy range. So these were since the beginning, the most promising things to look after for magnetar giant flare, but then we checked basically everything that could be done. So to do this, I used PIMS. So should be sure that that's correct. I take the flux expected for the beginning of the tail and then evolve it in time, add these pulsations, roughly 5 seconds period, and I simulate an observation by axis. This is from the galactic event. So you can see that clearly axis can detect the galactic magnetar giant flare tail, which is great. From the galaxy, this is rare, but according to the rates, we are kind of already late. We should have detected at this point another magnetar giant flare from the galaxy. So this could be possible. But now let's scale it outwards, how far we can see this and how far we can detect the pulsation. So these are the two questions. And to answer this, a series of simulations detect the spike in the Fourier transform and see what is the sensitivity, the significance of this detection. And here, the red band is 5 sigma. The orange horizontal dashed line is a 3 sigma. So we can see pulsations out to, say, 20 megaparsec, which is good. We can detect, of course, even further because we need less counts just to claim a detection, which could be still interesting. From nothing to something, it's a clue. So here is the more maybe the target plot for the question. So what is the time to target that we need to do this? And so here, how to read this. So axis can identify magnetar giant flare tail up to 20 megaparsec. If we repoint within 200 seconds. You need to detect pulsations instead. If you repoint in 150 seconds, you could see them out to 5 megaparsecs, so a little bit more constraining, but it's something. The last thing that I want to mention, and I'll try to be quick on this, because anyway, the answer, it's very cool, but the answer is that probably it's unlikely to see this. So in this plot, it shows very massive star in the disk of our galaxy. And in particular, there's the metallicity on the x-axis, with 0 being our sun, and the abundance of europium with respect to iron. Europium is one of the elements that can be reproduced mostly or almost exclusively in our processes. So kind of trace the our process enhancement element production from in these stars, our surrounding of these stars. So given that the metallicity also tells about the age, so higher metallicity is newer stuff. This trend means that there is something that enriched with our processes earlier on in the galaxy that cannot be explained by neutron star mergers, which are modeled with the dashed lines. This is because these events need to spiral, and that takes time. So there is a delay time since when you create the magnetars and they, or the neutron stars, and they're in spirals, and then they merge and produce the elements. So you need something that traces more closely the evolution of massive stars to explain this observation. And this could be very well magnetars. There was a recent paper in 2024 with the modeling on how magnetar giant flare could produce heavy elements. And the nice realization that was also recent is that we already detected that. It was already present in the data from 2004 magnetar giant flare. And so that decaying tail is the characteristic time decay from our processes. And they made study on that. And the conclusion is that magnetars, giant flare, accounting for the brightest one, they can explain 1 to 10% of the total required our processes in our galaxies. But something that we don't know is that even fainter events could produce the same yield of elements. They couldn't explain even the total of it. So we need more observations that can access help. The answer is unfortunately no. But these simulations, this current model that I just asked Patel to extend it to lower energies, doesn't account for K-shell transitions, for example. That could be important. So they might still look into this. I don't think the last word has been said on this. Okay, so these are basically, to recap the conclusions, kind of with the emoji smiles. I want to close with a more positive thing. Like, Axis is going to do great for magnetars. Not okay. I'm focusing on magnetar giant flares, but quiescent emission is very interesting to look at. The outburst, week-long emission is interesting to understanding ultimately the equation of state of magnetars. Burst storms are very interesting, and you can repoint when, for example, an FRB is detected. If this and stare for, I don't know, an hour or so, if in case this happened. There are dust scattering rings that have been observed after bursts, short bursts. So even if you don't detect short bursts, there are some magnetars that we know have dust clouds along in the line of sight. And so you can constrain that burst anyway. And they've been observed the magnetar nebula that also expand in time or evolve in time. So this is still time domain, an interesting case for magnetars. And I'll close here. Thank you.
Questions? Oleg, yeah, I'm gonna come up to the mic.
I just want to ask about possibility of studying future giant flares, or maybe not only future, that are in our galaxy, right? So there were some flares, not too many, from magnetars in our galaxy.
Yeah.
And there was, for example, an outflow detected in radio in expanding nebula, right, for 1900. And there's some attempts to look at X-rays, but maybe not that spectacular, because in one case, I think for 1806, HRCS was used for 20 kiloseconds, then XMM, but Axis can go much deeper. So what do you think? Is it maybe possible to detect some kind of nebula?
Yeah, I think so. So I know there are people looking into this. So that's not necessarily, time domain. So that's what we were focusing on, but that's definitely something to look at. Yes.
I had a question kind of from this plot. So you've kind of unified the different phenomena related to magnetars. And I guess you tell me, like the giant magnetar flares were previously unknown sources and they just happen to trigger all sky monitors?
This is a good question. I'm not sure if the magnetar was already known before the magnetar giant flare.
Well, my real question was like, has it, I mean, now there's been, you said 30 magnetars, so I guess seen in the initial outbursts, right? So like, have they ever, can we just monitor these sources and then hopefully like pick up a giant magnetar flare? Or is that like
that, the chance that happened, it's hard, but like this was kind of the point. So the short bursts can also be detected from Axis, even if they're very short, milliseconds. They're so bright that PIMS gets 1,000 counts.
Mm-hmm.
If you look at it. So the point is that we, with the galactic survey, you may or may not get them just because the magnetars are all located along the galactic plane. So you can get them. Maybe you can think about being inclusive of these objects in the galactic survey.
Mm-hmm.
There are some magnetars that are more active than others that we know. They are very active.
Yeah.
So you can look at those maybe more closely.
Okay.
and enhance the chance that that can happen. Yeah, so unfortunately, these bursts in the galaxy, yes, outside,
Yeah, okay.
they are too faint.
All right, good. Yeah. All right, let's thank Michela again. Oh, sorry. Yeah. No.
Yes.
Maybe, yeah. Okay, next up we have Wynn Ho, who's going to tell us about young X-ray pulsars.
Yes, so I'm going to talk about the one of the ways in which AXIS can have synergies with the high-frequency ground-based gravitational wave detectors that will be hopefully online at the same time. So I don't have a lot of time, so let me just get into it. So pulsars and in general neutron stars, they all emit gravitational waves. The key thing is that, and that's because they're not totally spherically symmetric. The key thing is, are they asymmetric enough to produce strong enough gravitational waves that we would detect them? Okay. But given that they emit gravitational waves, they are continuous sources of gravitational waves, unlike the transient sources that we've detected so far. Okay. Now, how the asymmetry of the pulsar can be from either like an elastic mountain or a magnetic mountain. They can also be from fluid oscillations. And the size of the mountain or the fluid oscillation basically scales directly to the gravitational wave amplitude, which is usually referred to as H naught. Okay. Now we can compare this this value, this as either this measured value, the gravitational wave amplitude, to what we call the spin down limit. Okay, and what the spin down limit is saying is that if the rotational energy loss, if this pulsar that's slowing down over time, so has a spin frequency and its spin rate, and it's decreasing over time because it's emitting radiation, so it has a new dot. If that energy loss is all due to gravitational waves, that gives us the spin down limit. Okay, obviously it's emitting electromagnetic radiation, so that's why we want to go below the spin down limit, because that tells us that what fraction of its energy loss is due to gravitational waves as opposed to other sources like electromagnetic radiation. So we want the measured value, H naught, to be below the spin down limit, HSD. Okay, that's what we strive to achieve and hopefully to detect. So in general, there's 4 different ways to search for gravitational waves from pulsars. And the first way is an all-sky search. Okay, these are for unknown sources anywhere in the sky, and they're the least sensitive because we don't know anything. So we have to, when we have the gravitational wave data, we have huge parameter spaces to search through. So that makes us the least sensitive. The next type searches is directed searches. Those are with sources that we know something about, for example, their X-ray flux or their age, in which we can then reduce that gravitational wave data search parameter space, right? And then there's the narrow band, and which we know the spin frequency and its derivative, but maybe not to very high accuracy. Okay, and then finally, the most sensitive searches are the targeted ones. Okay, these are ones where we know that's how fast this pulsar is spinning and how fast that spin is changing over time. Okay, and we get that information from electromagnetic studies from like the radio, gamma ray, or X-ray time tracking of that the pulses from the pulsar. Yeah. And so because we know that information, the spin frequency and the spin frequency derivative, that allows us to greatly reduce the searches through the gravitational wave data. It gives us the most sensitivity. Okay, so the current generation of gravitational wave detectors by LIGO, Virgo, Kagra, they have they're sensitive to gravitational waves at a frequency of roughly greater than roughly 10 hertz. Okay, and that's shown by the bottom right plot there. Okay, where it's plotting the gravitational wave amplitude h naught as a function of gravitational wave frequency. Okay, and the shaded kind of curve is the estimated average sensitivity of the current gravitational wave data run 04A, 8 months of it. Okay, and what you can see is that and that starts at roughly 10, 20 hertz. Okay, and you can see that's most sensitive roughly around 100 hertz. Right, tens, 80, 90 hertz to several hundred hertz. Okay, so if you consider pulsars, that means that you're basically ruling out, you can't, gravitational wave detectors can't look for pulsars that are spinning slower than roughly 100 milliseconds or 0.1 seconds. Okay, so what I show in the center plot, there's the PP dot diagram for pulsars, plotting spin P dot, spin frequency derivative, and spin period. And the shaded region up to the right, we can't look for gravitational waves from those. Okay, but we can look for the ones on the left. So radio and gamma ray timing could give a look at that includes several hundred of them, so we can look at them. But they're generally older pulsars. The ones that the radio and the gamma ray are looking at are generally older ones. Okay, but the X-ray pulsars are younger. Okay, they're hotter. And because as they're younger and the hotter, they may be more asymmetric, okay, because they have higher magnetic fields, for example, higher temperatures. They can give you higher asymmetries in the pulsar, so they can generate more stronger gravitational waves. Okay, and so we've been going on a campaign of monitoring timing X-ray pulsars for a while now using NICER. And I should emphasize that we're only looking at timing X-ray pulsars with NICER that are only observable in X-rays. So we're not looking at the radio ones or gamma ray ones because, why spend the valuable X-ray time when you can do it with a ground-based radio telescope? So we're only looking at X-ray only radio quiet ones, basically. So let me move on to talk about what can AXIS do, okay, with the next generation. Well, I hope that by the time AXIS is up, my hope is that we will have detected gravitational waves from isolated pulsars, and so I would be able to jump straight from searches to what are we learning about them into the bottom bullet point. As a theorist, that's what I would love to be able to talk about. But in lieu of that, the next generation of ground-based gravitational detectors that is being considered is Cosmic Explorer, mainly led by the US, and Einstein Telescope, mainly by the Europeans. Okay, and there's what I show in the middle plot there is, again, gravitational wave amplitude as a function of frequency. And you can see the 03 run and 05 sensitivities. And then the sensitivities of Einstein Telescope in 2 different configurations. And you can see that it's the sensitivity now much lower, so it can be more sensitive. It's more sensitive now. Then below that, I show you can see the comparison between Cosmic Explorer and Einstein Telescopes. They're comparable, but there's some differences and stuff due to designs and stuff. The main point here is 2 main points is that the next generation gravitational wave detectors will be much more sensitive. The other thing to notice is that will be sensitive to lower frequencies, right? So you could go down to, say, a hertz, right? However, you can still see that the shape of the sensitivity, it's still much more sensitive in the tens to hundreds of hertz. Right? So those are still your best chances of detecting gravitational waves from pulsars. Okay. And so young fast-spinning pulsars are still your best chance of detecting gravitational waves. And so what can AXIS do? Well, AXIS, so the young X-ray pulsars are young, so they're often in complicated X-ray fields. So like in pulsar Wynn nebulae, supernova remnants, globular clusters. And so what AXIS provides is a high spatial resolution so that you can get your pulsar signal much more easily. What you also need is, which I would push for, advocate for, is that if you want the fast ones, you need sub-millisecond time resolution, and you also need absolute time accuracies on the order of 10 microseconds. Okay. Obviously, shorter time even better time resolution, even better accuracy, even better. Okay. But that's kind of what you would need. And in terms of monitoring, so I've made the comparison with NICER, which is what we're using to time them. AXIS is, if you put in for each of the sources, what I did, I just took their spectral properties, put them into the PIMs, calculated what the count rate is for NICER versus AXIS, and we can monitor them in about half the time that NICER does. Okay, and actually that's a conservative limit because NICER is not imaging. It's getting a lot of background photons. So the pulsar signal is buried within lots of kind of quote unquote noise, right? Whereas AXIS would not have that, right? So the estimates of observing exposure time is an upper limit. It would actually be less than that. Okay, and the final point is that detection of gravitational waves from a pulsar would be transformational. Okay, it would be huge. Okay, and I'll just list a couple of things. I mean, we'd be able to find pulsars that are on the other side of the galaxy that we would not be able to detect electromagnetically. Right? And it provides us with unique insights into nuclear physics and particle physics, fundamental physics that you can't test in our labs and stuff. And I'll stop there. Thank you.
Okay, questions. I had a couple of questions actually. So if you did not have that absolute timing accuracy of 10 microseconds, but you had still millisecond time resolution in the smaller frame, would that be like, what would you not be able to do? Or what, would that still be interesting?
Well, yeah, absolutely it would be. So I guess I was kind of operating on the assumption of that you had presented that the windowed mode would have 10 millisecond time resolution, and then a continuous clocking of around 200 microseconds. Mm-hmm. So that's why I was saying that the 10 microseconds is for that 200 microsecond accuracy, or time resolution. So if you as you kind of push those time limits up, then I would say you're kind of restricting yourself from the faster spinning ones. Okay. So you have to go for kind of slower ones, but still fast enough.
Still good, maybe good enough in the Cosmic Explorer era. My other question is are the limits from LIGO interesting?
Yes, they're starting to be interesting. So can I back up? Okay, so what you see on the bottom right panel from the latest data is, so the spin down limit is the little gray triangles for each of them. Okay, and so so the point is that you want that average sensitivity to be above those limits. Okay. Sorry, below those limits.
Yeah, I see.
And so you can see, and I've highlighted the nicer ones. So we're already below the spin down limit for many of them. Cool. And so let me just point out. So for two examples, we're already saying for JO537 minus 6910 and 1849, Two of the ones that were timing were nicer, we're already restricting the gravitational wave component of the energy loss to several percent.
Cool.
And so that's telling us that, for example, the mountain on top of that neutron star is smaller than some, on those ones, it's around 10 to the minus 5-ish. Yeah.
Okay.
In
Awesome.
relative scale. Yeah.
Yeah. All right. Well, let's thank Wynn again. That was great. Thanks. Okay, I'll give you a 2-minute warning. All right. Next up, we have Joheen Chakraborty from MIT talking about quasi-periodic eruptions.
Hey, wiggle the mouse. Does it show up?
Yes.
Ah, cool. Okay. Ah, nice. Okay. Okay, great. Hi, everyone. I'm Joheen. I'm a grad student at MIT, where I work with Aaron and many other fantastic collaborators. And I'm excited to tell you about some recent progress in quasi-periodic eruptions, or QPEs, and what we hope Axis will do for pushing forward the study of these objects. So most of this talk kind of follows broadly a 2-page science document that we put together for this Axis science book that Aaron mentioned yesterday. So that's what's linked over there. So I like to start QPE talks by showing off an anthology of what we usually see when we study X-ray variability from accreting massive black holes. And the key takeaways from these light curves are that supermassive black hole variability in X-rays tends to be stochastic and pretty much disordered, with the characteristic amplitudes of 10 to 30% and characteristic timescales of kiloseconds. And this was very much the case in GSN 069, this other kind of peculiar but mostly unexceptional galactic nucleus, at least in 2010. But then Giovanni Minuti and his collaborators obtained follow-up monitoring of this source and were rewarded in 2018 with the discovery of a sort of totally new, unprecedented type of X-ray variability from this galactic nucleus. So this kind of birthed the field of QPEs, and it was an amazing kind of serendipitous discovery. Since then, astronomers have been hard at work trying to flesh out observations of QPEs and converge towards a theoretical understanding of what powers this phenomenon. We have now a population of about 11 sources, depending on how you count. Their gross kind of overall population average properties are that they tend to show peak luminosities of around 10 to the 43 ergs per second, with characteristic recurrence times of a few hours up to several days now. You can kind of see just from this example light curve that there can be quite a lot of scatter in the burst arrival times, but there is still an underlying stable clock mediating the system. And the duration of the bursts appears to scale with the recurrence time, such that the duty cycle of the bursts is about 10% in the sources that we know about. The emission, the X-ray emission at peak is soft and quasi-thermal with a black body-like spectrum, characteristic temperatures of around 100 electron volts. And acute surprise that kind of appeared shortly after the discovery of QPEs is that they seem to prefer to emerge in the aftermath of tidal disruption events. There's now a few sources that we know about where we see something like this, where there's a tidal disruption event discovered in optical. This is an example from ZTF that we found recently. And we saw in 2022 this initial optical and UV flare and only faint X-ray emission at the time of the initial disruption. But then over the course of a few years, as the optical and UV emission declined and the X-rays got brighter, we got some nicer high cadence monitoring and found the emergence of QPEs a couple years after the initial disruption. So to now skip several years and many tens of papers of hard work by many creative theorists, the leading class, or at least the most popular class of models for these objects, is that they may be powered by extreme mass ratio in spirals, or EMRIs. This is when you have a binary system consisting of a supermassive black hole and a much lower mass companion, so something like a star or a stellar mass black hole. As we all know, supermassive black holes often will have stuff around them, right? This stuff is kind of why many of us are gainfully employed. And these EMRIs, a couple times per orbit, will interact with these accretion disks. And it turns out that the energetics of the collisional shocked emission from these interactions is potentially a feasible explanation for what powers these QPEs. This is by no means kind of a confirmed or be-all end-all model, and we're still in the early enough days where it's worth exploring other ideas. But this is the class of models that's gained the most traction so far. So the first thing that's natural to ask is how can AXIS potentially help us widen the breadth of our sample of known QPEs? And I'll talk about two methods. The first kind of mirrors the way that many of the QPEs that we already know about have been found, which is through eROSITA. So Ricardo Arcodia, who's a postdoc at MIT that I work with closely, has led sort of heroic efforts to use the eROSITA all-sky survey, which has a terrific soft response and a scanning cadence of a couple of hours. To find this is kind of well matched to the characteristic timescales and properties of QPEs, and with this wide coverage of the sky, has found a population of these sources. And last year, he put together the first estimate of the QPE luminosity function. Integrated, this comes out to a formation rate of a little under 10 to the minus 7 per cubic megaparsec per year. For reference, this is about a factor of 5 to 10 lower than the tidal disruption event rate. So you can easily imagine, by having a kind of careful and cleverly designed survey strategy of pointing at the same regions of the sky repeated times with the right cadence, you can use AXIS to find blindly a sample of many, many more QPEs. And this is what he's done in this complementary QPE rates science case that I've linked here. The other method that I'll talk about is using this kind of extremely convenient fact that QPEs we're finding emerge in the aftermath of tidal disruption events, which TDEs themselves are intrinsically kind of rare compared to many other classes of transients. So this kind of dramatically decreases the sample space of galactic nuclei in which to look for these objects. And in this recent paper where we reported a third instance of QPEs following an optical TDE, we posed the question of, okay, we now know of order 100 optical TDEs total, and they have kind of this very widely varying range of X-ray follow-up so far. Given this, what is the likely fraction of these optical TDEs that may result in QPEs? And we find that it's something like around 9%, still with relatively wide error bars. But you can take this kind of Bayesian estimate and multiply it by the all-sky TDE rate, which is pretty well measured at this point, and arrive at roughly a consistent number with the independent all-sky survey. So given that AXIS will be taking place in the Rubin era, or even following Rubin, selecting some subpopulation of Rubin TDEs for dedicated X-ray monitoring is going to be it's going to be an excellent QPE finding machine. So we can also go deeper on known QPEs rather than just wider. So the dynamics of the shock breakout from this star disk collision are now kind of an exciting area of intense study. And recent work has suggested, recent Monte Carlo radiative transfer simulations have suggested that the ejecta, once it escapes from this disk, follows a roughly homologous expansion. So homologous expansion here just means approximately self-similar, and quasi-spherical expansion, it's an approximation used commonly in the stellar winds and supernova literature. And in a ubiquitous phenomenon observed in the spectra of stellar winds and supernovae is these P Cygni profiles with blue shifted absorption and red shifted emission. So we recently took advantage of the discovery of an extremely bright long duration QPE with exquisite signal to noise to find this first evidence for evolving P Cygni profiles in a QPE. This is, of course, a very dynamical system, and you can kind of track the time evolution of this ejecta, where we've taken a 2D slice here, and you can watch how the absorption profiles change over time. The qualitative features are that initially the absorption profiles appear and move towards higher energies, and then as this fixed mass dilutes over the course of many orders of magnitude and volume, the photosphere slowly begins to retreat, and then the absorption lines move towards lower energies before disappearing. So how does this compare to the actual observations? Here I've shown the spectral residuals over the course of one burst, and you can kind of see qualitatively this behavior that's expected. So it's kind of circumstantial and suggestive evidence, which is interesting. So Axis's kind of superior effective area, especially in the soft band, is going to be excellent for enabling these studies in many more QPEs than currently feasible. One of the exciting prospects of QPEs is that they may be dynamical probes of EMRIs in the LISA era. EMRIs are kind of this extremely convenient limit of the two-body problem in general relativity, because you can solve the problem analytically by treating the secondary perturbatively. And this is why they're kind of one of the main science pillars of the LISA mission. So the natural question is, will Axis or X-ray facilities in general give us a possible multi-messenger synergy with LISA? And the answer is probably not, at least for the known QPEs so far, although I think we're going to hear more about this in DJ's talk. The currently known sample of QPEs is at periods slightly too long to be LISA detectable, but it's still early days, and it's entirely possible that we find shorter period ones. But this means they can still be interesting and useful dynamical probes of their supermassive black holes. To give you some reference, I've shown the UCLA Galactic Center movie, and keep in mind that the shortest these stars have characteristic orbital periods of decades. I think the shortest period one in the yellow orbit is about 16 years or so. So that corresponds to about 100,000 RG around the supermassive black hole. QPEs suddenly potentially bring us a factor of 1,000 closer, and all of the amazing general relativistic precession effects, like the Schwarzschild precession of the periaps, becomes much more dramatic and high amplitude, and you can measure it over much shorter time scales in principle through this QPE timing. So I've recently been looking into how measuring QPE timings precisely encode information about the dynamics of this EMRI disk black hole system. And I think the most important facet that I'm finding is that the most important observational feature is that you want as long of a continuous observation as possible. There are all sorts of degeneracies that are introduced when you have large gaps in between QPE number. And with Axis's proposed L2 orbit, which will enable possibly stairs as long as 400 kiloseconds continuously or more, this kind of constrains the dynamics of this EMRI disk system by a factor of about 50% better than you can do with the current roughly 100 kilosecond XMM continuous exposure time. So it's natural to ask if this is kind of a theoretical possibility to use QPE timings as dynamical probes of their supermassive black holes. Has this been done already with the existing QPEs? And the answer is it's never quite that easy, right? The known QPEs appear to be messier or more complicated than would be predicted in this naive picture of a static in-plane accretion disk, which gives you an exquisite map of the apsidal precession. But by invoking a couple additional knobs, in this case by introducing a rigidly precessing accretion disk, which is kind of a generic expectation in tidal disruption flares, we were able to reproduce some observed QPE timings, as you can see in the bottom panel here. I think I'll skip this slide for a time. Okay, that's all I've got. Thanks for your attention.
All right.
Thank you, Joheen. Oh, wow. Lots of questions, but we don't. Yeah, go ahead, Javier. We can take maybe one or two questions.
I missed a little bit of the part where you were talking about the oxygen. I think it's emission and absorption at the same time. Is that, do you think this will explain the 1 kV emission that we saw, that the Megan saw in the 1S 1927?
Yeah, I think it's possible. I mean, there are a lot of parallels in like the properties and the energies at which it's observed. I would say the main difference in my eyes is that in this QPE, we see all of the line properties evolve over kilosecond timescales, whereas in 1ES 1927, I think they only change over longer timescales of months or so. So I don't think it's quite the same dynamical picture. But you know, there are some similarities to be drawn. Yeah.
One quickie. Yeah, Suvi, go ahead. Yeah, thank you.
So this modeling of the outflow from the collision, do you see sort of a bimodal distribution where you really can tell the difference between when it's intercepting the two different sides of the disk? So because that would really favor this model if you really saw a signature that
Yeah, we don't quite see something like that. You can kind of see from the bottom left panel there doesn't appear to be this like odd even behavior as is kind of expected from the QPE models. But I think there's other reasons why that source is more complicated, so we should chat about it afterwards. Yeah.
Okay. All right, let's thank Joheen again. Next up, we have DJ Pasham, who will also follow up with this story of QPEs.
All right, cool. Yeah, good evening, everyone. Good evening, everyone. Yeah, thanks for being here. This is late for you guys. So I realize I'm between you and dinner, so I'm going to try to be super quick. So yeah, thanks, Joheen, for the really nice overview of QPEs. I'm going to dive in and talk about something very specific relating to QPEs. And this is work done in collaboration with people at National University of Singapore, Shubham Kejriwal, who's a graduate student who's working there. So I'm going to argue that in order to maximize our chances of detecting multi-messenger signals from these QPE sources, we want to focus on these so-called golden QPEs. So this is assuming that QPEs are EMRIs. And I think that is a big if right now. There's no a consensus, I would say, and nowhere it is established that these are indeed EMRIs. So there's a big if, and the whole talk will assume that they are indeed EMRIs. And what I define as a golden QPE is something that has a repeating timescale of less than an hour. In a couple of slides, it'll become clear as to why this hour timescale matters. Because that is the timescale that we want these systems to have now, so that they move into the LISA band in 15 years from now. And how will these multi-messenger systems be different from LIGO sources? These would be continuous multi-messenger systems, as opposed to GW17017, which was just a transient that lasted for a couple of seconds. And again, this continuous data set is going to be just so much more richer than the few second data sets enabled by LIGO. And of course, AXIS, because of its sensitivity, along with clues from Rubin and Roman, as I will show in a little bit, can really unveil this population of so-called golden QPEs. So yeah, I'm just going to start off with showing you GW17017. Of course, everybody has seen this slide way too many times, but I think it's really important to remind ourselves how a single source has just changed priorities for NASA, how the whole TDAM community has been energized by this one event. So the power of single event, you should not underestimate. So of course, going forward, LISA is going to be sensitive to gravitational wave events, but for systems that are much longer, timescales of seconds to a few tens of minutes. And it will detect many kinds of gravitational wave emitting systems. The ones that are relevant for today's talk are these extreme mass ratio in spirals. But again, within the context of this talk, when I say extreme mass ratio in spiral, it's a massive black hole and some sort of a companion, which could be a star or another compact object. And again, here the stress is really on continuous multi-messenger signals from these systems. So this is just a sense of what the sensitivity curve for LISA would look like. As you can see, it's the frequency with something like 10 to the minus, few times 10 to the minus 4 down to 0.1 hertz. So the big question is, what do we need these systems to be, what do we need the periods of these systems to be now so they can move into this sweet spot right here? That is where the sensitivity is the best, right? So that is the question we were trying to answer. That's what Shubham was trying to do. So what he essentially did is he took catalogs of existing EMRIs, and then he back evolved them. So this is just showing you what he did. On the top panel, you see the back evolution of EMRIs going back to 2001. And the bottom panel is just the eccentricity of these EMRIs going back to 2001. The rightmost shaded area is where LISA will operate, 2037, 2041, roughly. And Shubham used a wide range of eccentricities, mass ratios, inclinations, all the sampling over a wide range of these different values. So the main thing, and this dashed line is 2024 when this paper was written, which is still relevant for 2025. So the main plot that we got out of this work is shown here. Let me briefly explain what this is showing. On the y-axis, you're looking at the luminosity distance, and the x-axis is the orbital time of these EMRIs now, when the paper was done, 2024. And this gray area, so every dot is an EMRI, and this gray area is our systems that are beyond X-ray detector capabilities, right? So this value of roughly 1 gigaparsec corresponds to 10 to the minus 14 ergs per second per centimeter square, which is roughly in line with what AXIS can do. So as you can see, the stars are the ones that have a signal to noise of greater than 15 with LISA. So if you take a histogram of that, what you find is that they peak around 2.5 millihertz. That is the orbital period. But again, the QPEs will have half of that because the EMRI is interacting with the disk twice per orbit, right? So the time scale that we need these systems to have now so that they can be detectable with LISA, assuming they're EMRIs, of course, is something like 0.5 millihertz. So that is on the order of 1,000 seconds, right? Yeah, 2,000 seconds. So yeah, so that's sort of the work that was done into that paper. But there are some caveats I should mention because I don't want to be all gloomy about it. So the caveats are the evolution was purely gravitational wave emission driven. And of course, as we just saw in the previous talk, these objects are interacting with the disk, right? They're interacting with the accretion flow. So that would be sort of a wet EMRI, and that is way more complicated to evolve. So we did not consider that in our paper. The second uncertainty is we considered one particular catalog of EMRIs from this classic paper, what they call the fiducial EMRI catalog. But they also talk about different kinds of EMRI populations that can exist depending on what physics you assume for how EMRIs are formed. So these two knobs can perhaps be turned to push the time scale from 0.5 millihertz to even longer, maybe, but that's just something I want to mention. But again, let's take at face value what Shubham has done. So the main point is if you really want to have these systems, the QPEs, detect gravitational waves, you really want the QPEs that have a time scale on the order of till the 1,000 seconds. So how can you detect something that repeats every 1,000 seconds? Well, the things, this is sort of the ideal telescope that you want for detecting a fast QPE system. You want soft X-ray coverage. As you just saw, these things are very soft. You need a large effective area such that you can detect the eruptions in just a few minutes, a few hundreds of seconds exposure. And again, you want continuous coverage to sample enough number of cycles and convince yourself that you are seeing something QPEs, something quasi-periodic. And yeah, the last point I want to make is that you also want to be very sensitive over a very dynamic range. You don't want to pile up for the bright events. And of course, for the fainter, farther ones, as you'll see in a couple of slides, you really want low background to be able to detect them. So here, I'm just going to show you some simulated 1,000-second so-called golden QPEs with Chandra HRC. Chandra HRC in principle can do it, but it would really be pushing it. So on the left side, I'm showing you how this 1,000-second QPE source would look like at a redshift of 0.05. On the right side is redshift of 0.1. And if I repeat the same thing with Axis, obviously things will look much, much better. On the left side, you see these eruptions being much brighter, and you'd be able to do time-resolved spectroscopy like what was shown in the previous talk. For fun, I also extended out to the redshifts higher, and this is with Axis on Axis at a redshift of 0.5. In principle, you should be able to detect it. And you can, again, go all the way out to redshift of 1. You might not be able to do resolve individual eruptions, but with some folding techniques, you can recover the period, yes. So as you can see with Axis, the amount of volume you'll be able to probe will be 100 times more than what Chandra can do right now with these systems. Again, this whole thing, the time scale of an hour or 2,000 seconds or 1,000 seconds is based on the assumption that you're detecting these QPEs now, and then in 15 years from now, they'll move into the LISA band. But again, Axis will launch in 2030s, so one would have to update this whole work. But again, that would only increase the pressure because you'll be really closer to LISA. That means the time scale for these QPEs would be even shorter. So it'll be shorter than 1,000 seconds. So how can we do this systematically? It was mentioned before that you can follow up TDs. And if you remember what Suvi was saying, we'll be detecting hundreds or even thousands of TDs. Obviously, we cannot just follow up every single one of them because that's just not practical. But perhaps we can take some clues from other wavelengths. So what has been found is that out of the 4 TDE QPE systems, there are some interesting multi-wavelength behavior that is unique to these systems. The first one is in the optical, they appear to have these extreme coronal lines. Sample are shown here, these iron lines. 2 out of the 4 TDE QPEs have these lines. So maybe one can screen on this, perhaps. Again, it's a small sample, but at least we're just beginning to see the clues of this. The other thing we've found is that, again, 2 of the 4 QPE systems, they have this rising IR echo. So in green here is the QPE system, and the others are just normal TDEs. So as you can see, the one QPE system here is showing this nice rising echo. And the basic idea is these QPEs would heat up the dust around it, and that would imprint the signal of rising IR echo. So the way I see this working in the future, again, on the x-axis is roughly time. So the optical would give us this catalog of thousands of TDEs. The infrared and the optical spectra of some of these would help us cut down and sub-select the ones that have rising echoes, the ones that have these coronal lines. And Axis can digest all this information and pick the nearest, perhaps, or the perhaps the nearest ones. And of course, once Axis detects any of these golden QPEs, the same data can be looked in LISA to see if there's any multi-messenger signals. So again, I just want to stress that the binary model is no way the only solution to this phenomenon. There are many other interesting disk physics proposals that have been put out there, and I think they're equally super interesting. This is just to give you a snapshot of many, many models that have been proposed out there. This is not even updated. There's a couple more since this slide. So I just want to conclude by saying, of course, a super exciting new class of systems. And if they are EMRIs, I think that our best chance of detecting gravitational waves is by focusing on the really short period ones. And AXIS can do it out to redshift of 1. Thanks.
Questions for DJ? Eric.
So this is really interesting. Is there kind of a sweet spot here? Because I didn't try to do the numbers in an actual calculation, but if you're talking about 1,000-second period, you're talking about the low energy, the low mass range, the low mass part of the range for TDEs as it is, because you don't get orbital times of 1,000 seconds from, for example, a Milky Way size black hole. It's simply too short.
So at ISCO for a 10 to the 6 solar mass black hole, it's like a minute, right?
Thought it was longer than that.
Sorry?
Okay.
Yeah, so
I thought
most
it
of
was
these are
longer
10 to the
than-
5, 10 to the 6.
Okay. Okay.
Richard, and we'll take Aaron. Come up, please.
So just a technical question. If you know the period, doesn't that increase the sensitivity of LIGO a lot?
Sorry, if you know the period, then what?
Doesn't that increase the sensitivity of LIGO a lot? Because you have a much smaller, you're not searching for a period. Because right now, isn't the LIGO sensitivity set up that you really don't know the period in advance and you have to search through a wide frequency range?
I think the answer is yes. I have not done that analysis myself. Wojciech, who's the co-author on that paper, did that. But I think the answer is yes.
Yeah,
you
'cause-
know, obviously it's not a blind search anymore.
Right. So I think that could be an important improvement.
I think this was considering the positions already, the signal to noise.
LISA sources. You talked about LIGO.
Sorry, Lisa, I'm sorry.
Yeah.
Okay. One L is another.
So yeah, I mean, you're in very different timescale regimes, right? Because the frequency range.
All right, let's thank DJ again. Next up, we have Aaron Pearlman. He really is our last thing between us and dinner, but we're excited for him to tell us about FRBs.
You guys entertain for a little bit while the hunger sets in. My name's Aaron Pearlman. I'm a prize postdoctoral fellow at McGill University. And I'm going to tell you today about FRBs and why I think AXIS is going to be a major player in the next phase of FRB science. Okay, so let's orient ourselves. What are FRBs? These are extragalactic coherent radio flashes. We don't know the origins of these objects, but we think they are compact based upon their short durations. They are extremely luminous with peak brightnesses of about 1 to 100 Janskis. And most of the sources are only detected once, about a few % or so are repeaters. And there's an enormous all-sky and volumetric rate of about 1,000 events per sky per day, distributed isotropically across the full sky. And there's numerous models that have been proposed to explain the origins of FRBs, ranging from magnetars, as we heard about from Michela, as well as accreting black hole systems, pulsars, other types of interacting binary systems. So there are many hundreds of models, and despite the plethora of data, we are still trying to figure out their origins. As I said, they're almost certainly related to neutron stars in some way, because we've seen some radio bursts that have durations between nanoseconds to milliseconds or so, which implies a extremely compact emitting region of less than 300 kilometers or so. And if we think about the objects in the known universe that we know about, neutron stars are one of the things that comes to mind. But of course, there are other more possibly exotic explanations. So here is a luminosity with radio transient phase space of FRBs. So the spectral luminosity is on the y-axis and duration is on the x-axis. And what you see is FRBs are on the top right, but there is enormous breadth of luminosities that just span the neutron star zoo. So for instance, SGR 1935, the well-known magnetar that produced an FRB-like burst in our galaxy, has been observed to produce radio bursts spanning something like 9 orders of magnitude in spectral luminosity. Another noteworthy example is this FRB 2020-0120E, which I'll talk a little bit about in a moment. This is the closest known extragalactic FRB, which sits at 3.6 megaparsecs. But interestingly, although it's the closest one, it on average produces radio bursts that are less luminous than other cosmological FRBs. And this is really pointing to observationally that there is perhaps a diverse range of sources that could explain the observed phenomena. Now, FRBs have so far, despite an enormous effort from the international community, been observed to be a primarily radio band limited phenomenon. We have looked across the full electromagnetic spectrum and so far have only observed radio emission between frequencies of 100 megahertz up to 8 gigahertz. And one of the major frontiers, I think, in the next phase of FRB science is building an instrument like AXIS, which has extremely high sensitivity, high spatial resolution to really probe the emission processes of FRBs and really answer the question, do they emit X-rays? Because these objects are extremely energetic. And we also want to understand what type of objects these things are. There seems to be some connection to magnetars, at least for a fraction of the population. And I'll switch gears a little bit towards the end about what can be done as we move into this era of many tens of thousands of FRBs and start pivoting towards doing cosmology with them and using them as cosmological probes and trying to look at the distribution of baryons on large scales and how that can be complemented by AXIS. Okay, so to sort of get ourselves in gear about where things are going with AXIS, we have to first understand the past, the present, and the future. So in the past, the FRB field was primarily driven by these small field radio telescopes like Parkes, the Green Bank Telescope, and Arecibo. These are diffraction limited single dish telescopes with high sensitivity but very narrow fields of view. And while they were extremely sensitive, their limited field of view made it very challenging to detect FRBs. Since then, there has been really an enormous revolution in the semiconductor industry that allows us to leverage new technology. Particularly graphic processing cards have really allowed us to do digital signal processing extremely inexpensively, both on a hardware scale and also on a computational scale. And also the cell phone industry, we can now purchase cell phones where we have RF amplifiers that only cost about $1. So combining those technologies allows us to really build a new type of telescope that is a wide field of view and also sensitive that allows us to search the sky for FRBs. This has really been driving the current phase of FRB science, where we have experiments like the CHIME FRB telescope, which is really the world premier FRB detector. And we also have the European VLBI network, which is an ad hoc network of radio dishes spanning across the globe, which has extremely precise localization capabilities for repeating FRBs. And then we also have other experiments like MeerKAT, ASCAP, and DSA 110, which are operating in a similar vein as a radio interferometer and leveraging those technologies. And we're now entering a new era where we can also build these long baseline outrigger stations coupled with CHIME as our as our world-leading FRB detector and use new types of VLBI technologies called synoptic transient VLBI techniques to not only detect large numbers of FRBs, but localize them to subarc second precision to their host galaxies. And this experiment is really underway as we speak. We're detecting FRBs and localizing them. So we have 3 stations, outrigger stations that work together to localize chime-detected events. One is called the KKO station, which is located in Western Canada. We have an outrigger station at the Greenbank Observatory near the GBT, and we just finished commissioning a 3rd outrigger station in Hat Creek, California, where the SETI Observatory is. And then in the 2030s, we'll also be encountering a new era where there'll be these mega FRB detectors like QUARD and DSA 2000 that are going to just based upon a detection rate, produce about 10,000 FRBs per year. And you can expect roughly thousands of FRB host galaxies from those experiments. QUARD, in addition, will have similar types of outriggers to CHIME. And that will enable, because it's at slightly higher frequency, up to 1.5 gigahertz, localization precisions down to 10 milliarc seconds or so. And you can also think in the far future. So what the field is also trying to move towards is building this full sky coherent survey where you can basically think of just carpeting the ground with antennas. While computers and technology are not quite there yet, you can imagine if Moore's law continues, then we may be on that path to building such a type of telescope that's a 4-pi steradian coherent FRB search engine. And there's some technologies that are already moving in that direction. So there's a telescope called BURST, which is a dipole array of antennas that just sits on the ground. And it has about a pi steradian field of view. And GREX is also another experiment that tries to see the full sky at lower sensitivities. So I'm going to transition back to focusing on FRBs and X-rays. I mentioned a bit about SGR in 1935. In 2020, we saw a mega Jansky radio burst, an FRB-like burst from SGR 1935 that really solidified the connection that some FRBs are likely produced by magnetars. And if such a burst had been detected from a nearby galaxy, it would have been indistinguishable from an FRB. And in addition to that, we also detected an X-ray burst that was contemporaneous with this radio burst, which is also showing that magnetars are not only producing FRB-like bursts, but accompanying X-ray emission, suggesting that perhaps some FRB-like sources are also X-ray emitters as well, really motivating the use of AXIS to do studies of FRB sources that are extragalactic. SGR 1935 has also recently been seen to observe these glitch-like behaviors, bracketing the time of FRB on the scale of a few hours, which is something we could search for with AXIS with its timing capabilities. These glitches are some of the highest amplitude glitches in the entire neutron star population, and suggesting that there could be a link between neutron star rotation and the FRB emission mechanism if a similar process applies to FRBs. Now, magnetars are not the only type of model that produces or is predicted to emit X-rays for FRBs. There are other models such as Eddington accreting systems like ULXs. There's also a class of sources called like far field sources or GRB-like sources where you have some relativistic shock that propagates into an upstream medium. And of course, there's also other types of magnospheric pulsar-like models where you expect some type of soft X-ray emission as well. So now I'm going to give you my take on what some of the most promising approaches are to searching for X-ray emission from FRBs. So first, you have to keep in mind that radio telescopes are much more sensitive than X-ray telescopes. Because of that, you really want to identify nearby sources using wide field telescopes and then use the most sensitive X-ray instruments to follow them up. And AXIS will be able to do that. It will be able to expand the horizon out to which we can detect X-ray emission from FRBs. So as a case study to kind of highlight what you can do, here's the nearest FRB, FRB 2020-0120E. This is a source we detected on the outskirts of the grand design spiral M81. It was subsequently localized with the EVN to a globular cluster on the outskirts of the M81 galactic system. And I led a study where I carried out a multi-wavelength campaign using more or less all the most sensitive X-ray and soft X-ray instruments, including NICER, Chandra, XMM, NuStar, etc. And what we aim to do is try to simultaneously detect a radio burst and cover it in X-rays. And because the source is so nearby, you can place extremely tight limits. So the plot on the left shows the limits that we place are in red, and the limits of repeating FRBs are in purple, and non-repeating FRBs are in green. And the improvement is something like 4 orders of magnitude just because of the proximity of the source and the exquisite sensitivity of the X-ray instruments used. And you're really getting into the regime of galactic sources, which are indicated by these blue points, SGR 1935, and this other Magnetar 1E1547, which has also been observed to produce FRB-like emission. And from this study, we were able to rule out a number of scenarios for the first time, like some types of SGR 1935 like intermediate flares, ultra luminous X-ray bursts. This is a class of transient phenomenon that has been observed from objects spatially coincident in globular clusters, persistent ULXs. It's really pointing to possibly a magnetar in a globular cluster formed via accretion-induced collapse or merger-induced collapse, or perhaps some type of supergiant emitting pulsar. So how did we go about making that conclusion? So Michela gave us a really nice overview of the different types of magnetar prompt emission phenomenology. So I won't dwell too much on it, but there are really 3 main types of magnetar emission. One is giant flares. These are the most luminous events, and they last for several hundred seconds or so. There's also intermediate flares that last for a few seconds with luminosities of 10 to the 41 to 10 to the 43 ergs per second, and also short bursts, which are a bit less luminous and also shorter in duration. And what we did was we took the catalog of known magnetar bursts, short bursts, giant flares, intermediate flares, and we asked the question, if they were produced from the globular cluster in M81, how many of those would we have detected? Can we rule out entire classes of these types of events? So one thing we notice is that these ultra luminous X-ray bursts, they sit well above our threshold by about order of magnitude or so. Most of the intermediate flares from magnetars are also well above our threshold, and we're also able to rule out extragalactic giant flares from magnetars as well. Now, the SGR 1935 X-ray burst is about a factor of 10 below our detection limit, but it's important to note that the plot on the right shows that that burst wasn't particularly fluent compared to other X-ray bursts produced by this particular magnetar or even others. And you might find that surprising given the high brightness of the radio burst, but it does allow you to make a statement about ruling out other types of bright X-ray bursts from an SGR 1935 like magnetar. And what I'm excited about with AXIS is that modest improvements in the sensitivity, which will be provided by AXIS, will really enable us to probe deeper into this parameter space of magnetar short bursts. We also looked at persistent X-ray emission from the source. So on the right is distributions of different classes of sources, ULXs, LMXBs, and HMXBs, and magnetars. And it shows their luminosity. And what we did is we used NICER, XMM, Chandra, and NuStar, and we derived persistent X-ray limits at a variety of times across the campaign. And our limits disfavor persistent ULXs, as I mentioned. It's hard to reconcile the observations with even transient ULXs or accreting sources with luminosity luminosity is larger than 10 to the 37 or 10 to the 38 8 ergs per second. And many of our limits are also below the X-ray luminosity predicted for a 1.4 solar mass neutron star accreting at the Eddington limit. And we can also rule out a fraction of Milky Way-like LMXBs with bright persistent emission. Okay, so that's one way of going about it. So you can look for nearby sources. Another way is to look for extremely bright FRB bursts. So this equation that I have highlighted in red basically relates the X-ray energy to the radio energy through a quantity called the X-ray to radio fluence ratio, which is denoted by eta. So what you can do is that there are a lot of repeating FRBs that are hyperactive, and they produce many bursts. And what we've seen is that they also have this flattening of the energy distribution, where sometimes they can produce fluent bursts that are like hundreds Jansky millisecond or even kilojansky millisecond. These are extremely bright bursts that allow you to really constrain the emission mechanism